An introduction about discrete time signal. The discrete signals is a function of a discrete independent variable. The independent variable is divided into uniform intervals and each interval is represented by an integer. The letter n is used to denote the independent variable. The discrete or digital signal is denoted by x of n. Representation of discrete time signal. The discrete time signals are represented by functional representation, graphical representation, tabular representation, sequence representation. We'll see one by one. The first representation of a discrete time signal is the functional representation. In functional representation, the signal is represented as a mathematical equation as shown. So here we take x of n. For x of n is equal to minus 0.5, 1, minus 1, 0.6, 0.5, 2 and 0. Okay, now these are the values of x of n for n is equal to minus 2, n is equal to minus 1, n is equal to 0, n equal to 1, n equal to 2, n equal to 3 and 0 for other n. Okay, so this is called the functional representation. Okay, so here we have a set of x of n. Now this is nothing but the amplitude of a signal for n instance. So at n is equal to 0, your amplitude is minus 1. At n is equal to minus 1, your amplitude is 1. At n is equal to minus 2, your amplitude is minus 0.5. So this is how it is written. We have done this for most of the problems. This is called functional representation. Next we'll see what an graphical representation is. The second is graphical representation. This is the second representation. Here in graphical representation, which is denoted by GR, the signal is represented in 2D plane, that is two-dimensional plane. The independent variable is represented in horizontal axis and the value of the signal is represented in vertical axis. Now, for the same functional representation example, we will draw graphical representation. So here x of n is taken in y-axis and the instance n is taken in x-axis. Okay, and you know the values of n. So it is 0, 1, 2, 3. Here it is minus 1, minus 2, minus 3. So these are the representations of n. Okay, next comes the amplitude x of n. So x of n is 0.5 at minus 2. So at minus 2 it is 0.5. Okay, then at minus 1 it is 1. At minus 1 it is 1. Then at 0 it is minus 1. At 0 it is minus 1. Then at 1 it is 0.6. So at 1 it is 0.6. At 2 it is 0.5. 0.5. At 3 it is 2. Okay, so now this is said to be the graphical representation of discrete time signal. The third representation is the tabular representation. In tabular representation, two rows of a table are used to represent a discrete time signal. In first row, independent variable n is tabulated, and in second row, the value of the signal for each value of n are tabulated. So let's see you have to draw a tabulation. Okay. The upper represents n and the lower represents x of n. Leave the first and the last block. Then it is -2, -1, 0, 1, 2, 3. And the corresponding amplitude -0.5, 1.0, -1.0, 0.6, 0.5, 2. So these are the same values which we took for graphical representation and functional representation. Okay, so this is called as tabular representation. The fourth is the sequence representation. So here you can have infinite duration and for finite duration. First we'll see for infinite duration. For infinite duration, the representation of x of n is -0.5, 1.0, -1, 0.6, 0.5, goes on till infinity. Now we have to draw the center point. So this indicates n is equal to 0. Okay, 1.0, this indicates n is equal to 0. Now if it's for finite duration, this was for infinite duration, next comes for finite duration. Then it will be -0.5, 1.0, -1.0, 0.6, 0.5, 2. Okay, and we have arrow in the center. Now this says n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3. Whereas on the opposite direction it is n is equal to -1, -2. So this is how it is represented in sequence. Okay, so we have seen 4 representation: tabular representation, sequence representation, graphical representation, and functional representation. Let's see a problem on discrete time signal. Plot the following signal if x of n 1, 4, 3, -1, 2 is given. Here 3 represents n is equal to 0. So this representation is called sequence representation. Okay, for the signal you're asked to plot x of -n -1, x of -n by 2, x of -2n plus 1, fourth x of -n by 2 plus 2. So these are the 4 different things that are asked to do for the given problem x of n. Okay, so first thing you will take down the values. Okay, solution: x of -2, x of -1, x of 0, x at 1, and then x at 2. So let's check out what are the amplitudes. For 0 it was 3, so it will be 4, 1, -1 and 2. So these are the amplitude that has been written. Okay, so please check and write the amplitude for each of the n instance. Then comes the first problem: x of -n -1. So -n stands for delayed shift. Okay, -n stands for delayed shift, and -1. -n stands for time reversal. So here a delayed shift along with the time reversal takes place. Now when we say delay shift, now your n becomes for n is equal to -3. Okay, delayed shift 1 towards the right. N is equal to -2, n is equal to -1, n is equal to 0, n is equal to 1. Okay, so the value will be minus 3 minus 1. Here it will be minus 2 minus 1. And then it will be minus of minus 1 minus 1. And then minus of 0 minus 1. And finally minus 1 minus 1. Okay, so the new values will be 3 minus 1, x of 2 minus 1, x of 1 minus 1, x of minus 1, and finally x of minus 2. The amplitudes, now this you can again simplify as x of 2, x of 1, x of 0, and these are the same, x of minus 1, x of minus 2. Now the values will be 2, minus 1, 3, 4 and 1. So for n minus 1, the new time instants are 2, 1, 0, minus 1, minus 2. And the amplitudes will be 2, minus 1, 3, 4, 1. 2, minus 1, 3, 4, 1. So having this, you are going to draw the representation. Okay. So how it will be? This is your 0. So at 0, it is 3. The amplitude is 3. Okay. Then at 1. At 1, it is minus 1. At 1, it is minus 1. Then comes, so we have completed at 1, at 0. Then comes your 2. So at 2, the amplitude is plus 2. Okay. And then comes minus 1. So at minus 1, the amplitude is 4. This is 4. This is 3. Here 2. And then finally at minus 2, it is 1. At minus 2, it is 1. So this is how x of n minus 1 is drawn. But the question asked is minus n. So again you have to do a time reversal. And once you do the time reversal, the new signal that has been obtained are okay, so this is the new signal. Which has been obtained after time reversal. All those signals will come here and this will go. Fine. So this is your x of minus n minus 1. So we have done the first problem. The second subdivision, x of minus n by 2. For doing so, first write the values of x of n. So from here you can write the values of x of n. Okay. So for x of n you will have x at minus 2 is equal to 1. X of minus 1 is equal to 4. X of 0, 3. X of 1 minus 2. X of 2, that is 2. So this I have written. Now here minus 2, minus 1, 0, 1, 2 are the instants, that is n. So at this particular, the amplitude is 4. The amplitude is 1, the amplitude is 4, the amplitude is 3. The amplitude is minus 1 and 2. Now all these I have written for x of n. Now let's write for x of n by 2. So whenever I said it's n by 2, you have to multiply by 2. Okay. So if it's n by 2, then it is expansion of x-axis. Okay, so you're going to multiply it by 2. So now your x will be minus 2 into 2. That is x of minus 4. Same amplitude. There is no change in the amplitude. Let me write the left hand side first. X of 1 into 2, x of 2 into 2. Okay. There is no change in the amplitude. X of 0, x of 2, x of 4. Amplitude is same. It's 4, it's 3, minus 1 and 2. Okay, so now this is for x of n by 2. And then we have it for minus n. So for x of minus n by 2, this is for time reversal. What you're going to do, you're going to write the same instant. That is x of minus, or you can rather interchange. Okay, you're going to multiply the whole thing by minus. So now your x of minus 4 becomes x of 4, x of 2, x of 0, x of minus 2, x of minus 4. There is no change in the amplitude. The amplitude is same. Now we have got for x of minus n by 2. Now let's draw. Okay. Here it's 1, 2, 3. 0, 1, 2, 3, 4, 5. 1, minus 1, minus 2, minus 3, minus 4, minus 5. Okay. So at 4 it is 1. At 4 it is 1. At 2 it is 4. At 2 it is 4. At 0 it is 3. So at 0 it is 3. At minus 2 it is minus 1. At minus 2 it is minus 1. At minus 4 again it's 2. So this is the signal for x of minus n by 2. Okay, we have done expansion and then reversal. All the things have been done and finally we have drawn. If you want, you can draw a separate signal for x of n. You can draw a separate signal for x n by 2. And finally, you can draw a separate signal for x minus n by 2. So this is the second subdivision. The third subdivision, x of minus 2n plus 1. Now, I have written x of n, okay. So it is the same thing, x of minus 2. Here minus 2, minus 1, 0, 1, 2 are the values of n. So for each values of n, the amplitude is given here. This represents n is equal to 0. I have been telling this on all the problems. Okay, so please don't forget. So this is the initial x of n. Now first we have to do x of n plus 1. So now we know there is a advance shift by 1. So when you have to do 1, the new value of x becomes minus 2 minus 1. This becomes minus 1 minus 1. This becomes 0 minus 1. 1 minus 1. 2 minus 1. So now your new value becomes x of minus 3, x of minus 2, x of minus 1, x of 0, x of 1. So it has been shifted towards left. An advance shift takes place. The amplitude does not change. So it is the same. Okay. If you want, you can draw a small diagram for this. Similarly, you can draw the diagram for this. Okay. Next is 2n plus 1. Okay. It is x into 2n plus 1. So now here the signal is getting compressed. So for every value of n, you're going to divide by 2. Now consider this value. Okay, consider n plus 1. So from this, do the next part. So x of minus 3 by 2. X of minus 2 by 2. x of minus 1 by 2, x of 0 by 2, x of 1 by 2. Okay, the value is x into minus 1.5, x into minus 1, x into minus 0.5, x into 0, x of 0.5. So these are the new values of n for which the amplitude remains same. There is no change in the amplitude. Finally, we have to find for minus 2. Now this minus 2 represents time reversal. Okay, the minus in front of 2 represents time reversal. Okay, so for that, what you have to do? Multiply everything by minus. Multiply everything by minus. Okay. So when we multiply, this becomes x of 1.5. Amplitude is 1. X of 1. Amplitude is 4. X of 0.5. Amplitude is 3. X of 0. Amplitude is minus 1. X of minus 0.5. Amplitude is 2. Now, this is the value that has been obtained for x of minus 2n plus 1. Now, let's draw the graphical representation. This is your n. 0, 1, 2, 3, 4, 5, minus 1, minus 2, minus 3, minus 4. First is 1.5. So 1.5 lies somewhere here and the amplitude is 1. Next is x of 1. Amplitude is 4. X of 1, the amplitude is 4. X of 0.5 here. 0.5. Amplitude is 3. At 0, it is minus 1. At minus 0.5, it is 2, plus 2. Okay, so now here you get a compressed image that has been shifted in advance. Also a time reversal has taken place. Okay, so when you solve a problem, for each step you can draw a different graphical representation. For this you can draw x of n, for this you can draw xn plus 1 and then x into 2n plus 1 and then the final. Here I have only drawn the final graph. This is a method, but if the question is asked for 4 or 6 or 8 marks, you can draw the graphical representation for each and every step. So this is the third part of the problem. Fourth subdivision. Plot the following signal x of n. The sequential representation is given and you're asked to solve it. X of minus n by 2 plus 2. Okay, so now here x of n value I have already written. Okay, once again I'll repeat, these are the amplitude value. Here minus 2, minus 1, 0, 1, 2 represents the n value. So x of n is written. Next is the shifting. We'll do a shifting part. So plus 2 means advance shift. So x of n plus 2. When we say plus 2, then you have to subtract 2 from all of these. So x minus 2, x of minus 1, minus 2, x of 0, minus 2, x of 1, minus 2, x of 2, minus 2. Now the new values will be minus 4, x of minus 4, x of minus 3, x of minus 2, x of minus 1 and finally x of 0. 1, this is the amplitude value which does not change. Okay. So this is for x of n and this is for n plus 2. Since it is a shift in advance by 2, we are giving it as minus 2 and the resultant is here. Okay, so the signal which was supposed to start at minus 2 will now start in advance at minus 4. Next comes n by 2. When we say n by 2, that is time scaling. That is, you will have an expansion of signal. Okay, so x of n by 2 plus 2. We will consider this signal. Now we are going to consider this signal. Okay, so when we say n by 2, you're going to multiply all the values by 2. So x of minus 4 into 2, x of minus 3 into 2, x of minus 2 into 2, x of minus 1 into 2, x of 0 into 2. So the new obtained instances are minus 8, x of minus 6. See, the signal is getting expanded. X of minus 2, x of 0. But the amplitudes don't change. The amplitudes remain as it is. Okay, so this is the value of x of n by 2 plus 2. Then comes your time reversal. There is a minus sign. Don't forget that. That is the last step. X of minus n by 2 plus 2. Okay, so for this, you're going to multiply each instant with minus. So this becomes x of 8. I'm multiplying it and then writing it. Minus 6 into minus 1. Okay. Once again, I'll repeat, there is no change in the amplitude. The amplitude remains constant. Okay. So these are the final values obtained. Now for this, we can draw the graph. N. X of, we'll write it in the end. Okay. 0, 1, 2, 3, 4. We will need it till 8. 5, 6, 7, 8, 9. We won't go for minus because there is no value. So we won't plot it, just leave it. Okay, now plot the amplitudes accordingly. So x of 8 is 1. X of 8 is here. The value is 1. 1, 2, 3, 4. Next, x of 6 is 4. X of 6 is 4. 4. X of 4 is 3. X of 2 is minus 1. So take it down. Then x of 0, 2. So this is the final graph. And this graph is for x of minus n by 2 plus 2. So this is how all the problems in discrete time signal have to be solved.